Okay. Hey, Shotgun kids. So today we're going to simulate radioactive decay with pennies. Okay. Who remembers what we call atoms of the same element, but they have different numbers of neutrons? You just did your highlighting. Begins with an I. Begins with an I. I-S. Isotope. They're isotopes, okay? So there are two kinds of isotopes, the ones you start out with and the ones you end up with. Who remembers from the reading what those two names are? Ben?
The parent one and the daughter.
Parent and the daughter. Which do we start with? We start with everybody the parent and end up with the daughter. So today, representing the parent isotope are your pennies with heads. Will you please put all of your pennies in your cups? So these guys have a cup with 100 pennies, and I'd like you to do the same thing back at home. Okay, so the next thing is we have to record how many parent isotopes we're starting with. So how many are we all starting with? 100. So I'm just going to fill in 100 for you, and after this, you're going to be filling in your own numbers. So after one half-life, which is the amount of time it takes for half of the parent to decay to the daughter isotope, we're going to find out by shaking the pennies. Okay, so after one half-life, you will have half the amount, approximately half the amount. Let's see if that happens for you. I am going to have you guys in just a second shake the pennies up, and then I want you to pour them on your tray, and you're going to count how many parents you have left. Which ones are the parents, heads or tails?
Heads.
Heads. Okay, so you're going to shake, and you're going to count how many parents you have left. Once you find out, you're going to come and record it on the chart in front of the room under your group number. Are there any questions about that? Okay, hang on. Okay, you may begin. You guys at home should be doing this too. Okay, and we're back. So the students have shaken the pennies out, and they put the number of heads that are up here. Are these numbers far away, or are they pretty close to each other, guys? Pretty close. 49, 53, 57, 55, 51, 50. Those are very close. This is a half-life. It's the time it took for about half of the parent to decay to the daughter. Now what you have to do, don't do it until I tell you to start, you're going to put aside your daughter isotope, which are your tails, and you're going to put the remaining heads back in the cup. And you're going to shake it again, and then count and see how many are heads and record it. You guys at home do that too? Please begin. You put the heads back in the cup, put aside the daughters. So now they are returning the heads back to the cup, and then they will shake it again. And then shake and count. Okay, Shot Connect kids, look at the results. So what we have here now is a series of numbers ranging from 23 to 29. So I'll talk about those in just a moment. Okay, everybody, that was really great. So now we're down to the remaining heads. Let's take a look at percentages here. After our first half-life, about what percent of the parent remained?
50.
About 50%. Good. After our next half-life, about what percent remained?
25.
About 25%. Any predictions on the next percent?
I believe it's going to be about 14.5.
14, what do you think?
Yeah, like around 13.
Around 13.
12.5.
12.5 exactly. Okay, let's see what happens. From here on out, you're going to repeat the procedure until you run out of pennies. Let's review what you got to do. You shake out the parents, count only the parents, record, and then put the parents back in and keep shaking and recording. Go. Okay, so these are great numbers. As you can see, every time we had half of what was left, that's called a what life? A half-life. And some of you guessed that the next percentage would be 12.5, and that is pretty much right. So Jack, you were right on. On average, if you do thousands, millions of pennies, you're going to end up with those percentages. Let's look at these as fractions, though. 50% is what fraction, people?
Half.
So 1/2 of the parent has gone away. And then half of a half is a quarter. Half of a quarter is
1/6.
1/8.
1/8, and et cetera, et cetera, et cetera. So the math problems we're going to do today involve these fractions. If you know the percentage of daughter, or if you know the percentage of parent of a rock, you can tell how old the rock is. So we're going to do something called radiometric dating math problems. That's a separate part of this lesson. I'm going to pause it, get my PowerPoint on, and then we will start that lesson. So let's hang on. All right, so now let's solve some radiometric dating problems. You guys at home, you need your sheet out. It looks something like this. Radiometric dating problems, that's what your sheet is. So if you don't have it, get it out. Problem number 1. A crystal contains a radioactive isotope that has a half-life of 10,000 years. I need to pause for a second, please. Okay, sorry, some kids couldn't see, so I just moved them. Okay, a crystal contains a radioactive isotope and that has a half-life of 10,000 years. And to remind you, radioactive means it's unstable. It doesn't want to stay. It wants to go from parent to daughter. It's unstable. That's radioactive. 1/4 of the parent isotope remains in the sample. How old is the sample? Anybody want to guess? Yep.
2,500 years.
Okay, let's see. Let's see how it works. So what is the half-life? Look at the information I gave you. What is the half-life of this crystal? 10,000 years. So you write in 10,000 years. What is the half-life?
Oh, I did 1/4 of the half-life.
Okay, write that down. Then, how many half-lives have gone by? Well, we know that 1/4 of the parent isotope remains. So after our first, we start out, the white is all parent, okay? It's all parent. So after 1 half-life, we have half of that remaining, all right? But do we want half or a fourth? We want a fourth. We want 25%. So after that half-life, we have this many remaining. We have 1/4 of the parent isotope remaining. So how many half-lives are gone by? Take your finger and do this, or take your pencil and draw a line like this. From this box to the, I'll draw it here. Take your pencil and draw a line from here to here and count 1. Say it.
1.
Take another pencil and count and draw, say 2. Once you've got 1/4 of the sample left, or 4 squares, you stop. How many half-lives do we do?
2.
2. So it's 2 half-lives. So how old is the sample? Well, from here on out, it's easy. How old is the sample? It's 10,000 years times 2. 2 half-lives. If the half-life is 10,000 years and 2 half-lives went by, 10,000 years times 2 is 20,000 years. Okay? We will do 8 of these problems together. Second one. Wait, 8? Second one. Okay, 6 problems. Radiometric dating problem number 2. We have a crystal that contains a radioactive isotope, meaning it's in decay. It's got a half-life of 10,000 years. 1/2 of the sample remains, 1/2 of the parent isotope remains in the sample. How old is the sample? We're going to use the same procedure every single time. We want to stop in the boxes when we get half of the parent isotope left. So, what's the half-life, everybody? 10,000 years. Write it, please. To figure out the number of half-lives, we start with our full parent, and then we have, after 1 half-life, half remains. Tell me when to stop.
Stop.
We stop. We've got left. So take your pencil and draw from here to here. From here to here. How many half-lives is that?
One.
One half-life. Now to figure out how old the rock is, you have to multiply the half-life times the number of half-lives. So we have 10,000 years times 1, and that equals 10,000 years. God bless you.
Thank you.
Any questions on that one? Is it easy or hard?
Easy.
Yeah, it's easy. Would it be easy without the lesson?
No.
I tried to find a way for you. If you need to get your medicine, you may do that. Okay, third problem. Number 3. We have a crystal. It contains a radioactive isotope that has a half-life of 20,000 years. 1/4 or 25% of the parent isotope remains in the sample. How old's the sample? Here we go. Starting again, the question I'm going to ask is, what's the half-life?
20,000 years.
20,000 years. Good. And we have to see how many half-lives have gone by. What do we want to end up with? We want to stop when we get to
1/4.
1/4. So here we go. We have our full, then we have our half left here, and then we have our 4. So we stop.
Yep.
Take your pencil and count with me. Ready? 1,
No.
2. So how many half-lives? 2. And just, oh, I'm sorry. You guys, are you coloring those in?
No.
Okay, let me.
No.
Yeah.
I should have told you you were supposed to be coloring those in.
Yeah, I'm coloring them
Oh,
in.
good.
I'm not.
How many are coloring? Okay, you figured that out, right?
Just like a pencil.
With your pencil, yeah. You just color in the black. Just sketch them in. I'm sorry, those of you at home, you should be coloring where it turns blue. Okay, and so now we know easily you multiply the half-life by the number of half-lives. So how old's the sample? 20,000 years times 2 equals 40,000 years. All right, I'm going to stop it right now because these guys and you at home are going to do the rest of the problems by yourself, and then we'll come back and correct. Okay, here we go. All right, let's check and see how you did. First of all, if you think it was easy, say, I think it was easy.
I think it was easy.
If you thought it was hard, say, I think it was hard.
I think it was hard.
Oh, there we go. We have one. Good. So I hope this system works for you. We're going to do it again on Wednesday. We're going to review it during our test review, and I think you won't have any trouble. You'll see a few of these on the test. So the next problem was that you had a radioactive isotope with a half-life of 1,000 years, and 1/8 remains. So your half-life was 100,000 years. If you get the answer, say check.
Check.
The half-lives, we had to go to half, to quarter, to an eighth. So how many half-lives was that?
Check.
3. It was. Well, you said check before I counted the things. There were 3 half-lives. Okay.
Check.
And you multiply 3 times 100,000, and you get 300,000 years.
Check.
Check. Good. Next one. Hang on, folks. All right. Number 5. Radioactive isotope. It's got a half-life of 600 million years, but we only have half the parent, so we don't have to go back very far, right? So, how old is it? Well, what's the half-life, everyone?
600 million years.
Half-life is 600 million. And how many half-lives? We're only going back halfway, so it's 1 half-life.
Check.
And that's a check. And in order to find out the age of the sample, you simply multiply this times this, and you get 600 million.
Check.
All right, next problem has to do with carbon dating. We have a fossil bone. Remember, this is stuff that's more recent, more organic things. The half-life is 5,730 years. 1/4 of the parent isotope remains, or 25%. So what's our half-life?
What? 5,000.
5,730 years.
Check.
We need to go back to 1/4 of remaining, so we have 1/2. 1/4. How many half-lives is that? 2. Check. And so you multiply that times that to get the age of the rock, and that turns out to be 11,000 years.
Check.
If you got them all correct, say all correct.
All correct.
Wonderful. Okay, we're going to stop that lesson right now. I think the directions told you what you have to submit to me.